Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the EMT previous year questions of IES in a very detailed manner of electrical engineering. If you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever we upload a new video, the direct notifications comes to mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. Now we are going to solve the 41st question. See the question here. The field strength at a point of finite distance from an infinitely long straight uniformly charged conductor is obtained by considering the radial component and also the longitudinal component of the forces acting on a unit charge at that point. So by the charges on the elemental length of the conductor, the resultant field strength is. So basically here they are given a infinite long straight wire, and also we have to find at any point what is the net amount of electric field because of this long straight wire. We need to figure out based on the two components which are the radial components and also the longitudinal components. So based on these two components we have to figure out what is the net amount of electric field at any point in space. So out of these four options, option A is the correct solution of this question, which is the sum of R components or the radial components, whereas the sum of the L components or the longitudinal components is 0. So now we'll discuss the solution of this question. So option A is the correct solution of this question. So let's solve this numerical. So basically this is a very much infinite long strength wire, and I am going to take this as the origin, and this is a point P. So the distance between the point P and this line is called as the perpendicular distance, which is the rho. So rho is the perpendicular distance between the point P and also the origin, which is O. So now what I am going to do is I am going to take a small element at a height of Z. At a height of Z, I am going to take a small amount of length, which is dl. So because of this, a small amount of dl, there will be a small amount of point charge. So because of this point charge, it is going to act in the direction of the distance. So the distance between this elemental charge and the point P is in this direction. So therefore it is going to radiate the electric field in this manner. Let me assume this is E1. So E1 we are going to do the component in the radial direction and also in the longitudinal direction. So therefore the components are, this is called as the radial direction, which is E1R, and this is called as the longitudinal E1L. So if you take the same at a same amount of equal distance in the negative direction, there will be another component which is called as the dl. So this is in the another down direction. In the negative direction, same distance in the downward direction, there is also a small amount of dl. So if you join the distance between this dl and the point P, it is also going to radiate the electric field in the direction of the r bar vector. So here also the vector will be same in the upward direction. Here it is E2. And here, because the distance is same, so therefore we can say the amount of electric field intensity will be same. So E2 is nothing but is equal to again E1, because same amount of electric field. So if you take the component in the radial direction and the longitudinal direction, this will be in the same direction as the previous one, which is E1R again, and this will be again now E1L. So if you take these two components, these are equal in magnitude and also in the opposite direction. So therefore net amount of electric field in the longitudinal direction is equal to 0. But whereas the components of both the vectors in the radial direction are in the same direction. So therefore net amount of electric field will be always in the direction of the radial, but not in the direction of the longitudinal. So we can simply say that the net electric field is in the direction of the R components, whereas the longitudinal components are going to get cancelled out each other, and the net amount of electric field in the longitudinal direction is 0, but it is non-zero in the direction of the radial direction. So this is the meaning of the net amount of electric field at any point in space whenever we are going to consider the infinite line charge. This is the concept. See, now I will give you a small amount of formulas which are very useful in solving the questions. Suppose there is a finite length of 2a, where 2a is the finite length, and now I am going to take a point P which is at a distance of perpendicular distance from the line, which is rho. Then I want to find what is the electric field intensity at this point P because of this finite length charge. So now I am going to consider an angle θ1 and also θ2 from the origin O. So this is the angle, this is the length A, and this is also length minus A. This is in the downward direction, and this is the distance is rho. So the net amount of electric field due to any infinite or finite length will be always in the radial direction. So therefore we can say aero cap. So the electric field intensity formula, which is rho L by 4 pi epsilon rho into sin θ2 minus sin θ1 aero cap. Here sin θ2 is equal to rho by A by under root over A square plus rho square, and sin θ1 is equal to minus A by under root over A square plus rho square. So if you substitute sin θ2 and sin θ1 in this formula, and if you do the simplification, we are going to get finally E bar is equal to rho L by 4 pi epsilon rho into 2A by under root over A square plus rho square aero cap. So this is the net amount of electric field because of finite length charge at any point in space. Suppose I am going to consider no special conditions. If the length is very infinite, if the length is very infinite means simply we can say 2A is equal to infinity. It means θ2 will become plus infinity and θ1 will become minus 90. So θ2 will become plus 90 degree and θ1 will become minus 90 degree. And if you substitute these values in this above equation, finally we are going to get θ2 is equal to plus 90 and θ1 is equal to minus 90. If you substitute in this basic formula and if you do the simplification, finally we are going to get E bar is equal to rho L by 2 pi epsilon rho aero cap. So this is the net amount of electric field at any point in space whenever we consider an infinite line charge. And in the third condition, suppose I am going to consider the point B is at the edge of the one of the infinite side. So the remaining side is infinite, but the point P is at the edge of the other point of the line. So therefore we can say now what is the net amount of electric field at point P. If you see clearly here θ2 is equal to 90 degree and θ1 is equal to 0 degree. So substitute these values in the general equation. Then finally we are going to get E bar is equal to rho L by 4 pi epsilon rho aero cap. So if you know the general formula, you can apply the special conditions and then you can easily get the any special condition formula you want to figure out. And also I will discuss the important formula of the circular disc. What is the net amount of electric field because of circular disc at a distance of h from the center of the disc I want to figure out. I will give the expression, so it will be very useful in order to solve any numerical. Suppose now there is a circular disc, a charged circular disc, and then I want to find what is the net amount of electric field at any point in space because of this charged disc. I am going to consider the expression. Suppose this is a finite surface charge, circular charge, then or we can say finite circular area of circular disc, then what is the net amount of electric field at a point P which is at a distance of h from the center of the disc, and A is called as the radius of the disc. So based on these parameters, and rho is called as the surface charge density of this circular disc. So based on this data, I want to figure out what is the value of the electric field at any point in space. Then the expression E bar is equal to rho s h by 2 epsilon into 1 by h minus 1 by under root over a square plus h square into az cap. And if you see clearly here, this is called as the expression of the electric field at the point P. But I want to consider a special case where if the area of the circular plate is very large, means we can assume it is going to have some infinite surface charge density, or we can say infinite area. Then what is the net amount of electric field at the point P? So the assume is here we have to assume that A is equal to infinite, means it is going to have a huge amount of radius. Then what is the net amount of electric field at point P? And if you substitute A is equal to infinity here, 1 by infinity is value 0. So here this is the only thing which is going to remain, and it is going to get cancelled. So finally we are going to get rho s by 2 epsilon into az cap. And if you see clearly here, the electric field expression in this is independent of distance from the center of the disk. So it is independent of h. So we can say that no matter whatever the position you are at from the center, the electric field intensity will be always same. That is the reason whenever you are going to consider an infinite area sheet, always the electric field is independent of the distance from the center of the disk. No matter wherever you are, the net amount of electric field experienced by that point is always same. But if you consider a finite area, or we can say finite radius, then definitely the electric field is going to depend upon the distance you are going to present. If the distance is less, the electric field intensity is higher. If the distance value is increases, then we can say the electric field intensity is goes on decreases. So these are the, so by these expressions most of the questions are going to base. That is the reason I told you the expressions in order to remember to solve the questions. So now we are going to solve the 42nd question. See the question here. Three equal point charges are located at the vertices of an equilateral triangle on the circumference of a circle of radius r. The total electric field intensity at the center of the circle would be. So here they are given an equilateral triangle and also three equal point charges are going to present at the vertices of this equilateral triangle. And based on this, we have to find what is the amount of net electric field at the center. At the center of this triangle, we need to figure out what is the net amount of electric field intensity we need to figure out, and the circumference of this circle is nothing but it is equal to r. So based on this data we have to find what is the net amount of electric field at the center of this triangle, equal triangle, we need to figure out. So out of these four options, option A, which is 0, is the correct solution of this question. So let's solve this numerical. So basically here this is a equilateral triangle. So in the equilateral triangle, at each and every point of these vertices there is an equal amount of charge q. So now based on this equilateral triangle, in equilateral triangle always the circumcenter, the incenter and the centroid all are going to be at the same point. So based on this data we have to find what is the net amount of electric field at the center of this circumcircle, or we can say that at the center of this triangle we have to find what is the net amount of electric field. So because here the distance between the q and the center is r, so therefore we can say the electric field because of this charge q is re. So and here also the charge q and the center is same distance as r, and here it is going to radiate the electric field in this direction e, and the distance is same, so therefore the electric field intensity is also same. Similarly from this point to this center the distance is same as the previous one r, and it is going to radiate the electric field in the direction. So this is the electric field E. So if you see clearly that these are the three equal magnitude values, but these are the vectors. So therefore we can say the angle between them is this is 120, this is also 120 and this is also 120. So overall angle close is nothing but 360 degree. So based on this we have to find what is the net amount of electric field at the center of the circumcircle we need to figure out. So we can figure out the net amount of electric field in both ways. See, if you see clearly, I am going to draw this diagram, vector diagram here, which is E, this is also E and this is also E. But if you see clearly the angle between this E vector and E vector is 120 degree. So I want to find what is the net amount of electric field because of this E and E. So therefore if you know the parallelogram law, the net amount of electric field is equal to under root over E square plus A square plus 2E square into cos of 120 angle between them. Cos 120 is nothing but minus half. So therefore this 2 is going to get cancelled, and this E square and minus E square are going to get cancelled. Finally under root over E square is equal to E. So therefore because of these two vectors the resultant vector will be in this direction with the magnitude of E. But if you see clearly these two vectors are opposite and the length is also same, so therefore they are going to get cancelled out. So therefore finally the net amount of electric field intensity is equal to 0. So now this is the correct solution of this question. So therefore net amount of electric field intensity is equal to 0. You can go by the another method also, which is the vector directly. Here the net amount of electric field is nothing but it is a vector addition of the three vectors. So I am going to assume this as a reference. So therefore E bar plus, and it is rotated by 120 degree anti-clockwise. So therefore this will become a E bar, and this vector is rotated by 240 degree in the anti-clockwise. So therefore this vector will become a square times of E bar. So you can take the E bar as a common. So finally you are going to get 1 plus A square. So here A is equal to 1 angle 120 and A square is equal to 1 angle 240. In generally we know that 1 plus A square is nothing but 0. So E bar into 0 is again 0. So you can go by any of this method. Finally the solution you are going to get E bar net is equal to 0 at the center of this circle because of these three equal point charges. So this is the correct solution of this question. Now we are going to solve the 43rd question. See the question here. The dielectric strength of rubber is 40,000 volt per millimeter and at frequency of 50 hertz. So what is the thickness of the insulation required on an electrical conductor at 33 kV to sustain the breakdown. So basically here they are given a voltage of a conductor of 33 kV. So based on this also they are given the dielectric strength of this rubber of this above the conductor, which is 40,000 volt per millimeter at a frequency of 50 hertz. So what is the insulation we are going to require based on this conductor with the given data we need to figure out. So out of these four options, option A 0.83 millimeter is the correct solution of this question. So let's solve this numerical. So in the question they are given a conductor. This conductor is going to have a voltage of 33 kV, and also they are given a rubber. The rubber is going to be used as a insulation for this conductor. See, this rubber is going to have the electric field, or we can say the dielectric strength, means E is equal to 40,000 volt per millimeter. So therefore they are given the dielectric strength of this. The dielectric strength of this rubber is nothing but 40,000 volt per millimeter at a frequency of 50 hertz. Then based on this data we have to find how much amount of thickness of the insulation we are going to require, means how much amount of thickness of the rubber we are going to keep over the conductor in order to make it as a, means this is going to protect this conductor from external. So therefore if you touch this conductor from outside you are not going to get shocked, because this dielectric is going to behave like an insulator. Means dielectric is also called as basically an insulator. If you operate the electric field below this one, otherwise what is going to happen, if you operate the electric field more than the dielectric strength, then definitely this rubber is also going to behave like a conductor. So listen one thing, nothing is a perfectly insulator. So if you exceed more than its dielectric strength, then that insulator or the dielectric is also going to behave like a conductor. That is the reason if you operate the electric field below the dielectric strength of any insulator or dielectric, it is going to behave like an insulator or dielectric. But if you operate more than the dielectric strength of any insulator or material, then definitely that material is going to behave like a conductor. So therefore the current is going to get passed through that materials. So based on this data we have to find how much amount of thickness of the insulation we need to require. So basic formula, electric field is equal to voltage by distance, or distance is the thickness of the insulation. So electric field they have given already 40,000 volt per millimeter is equal to voltage value is 33 kV by T. So volt to volt is going to get cancelled, and if you take this T here, so therefore this value you should take the downward and do the simplification. T is equal to 33 into 10 to the power of 3 by 40,000 millimeter. So based on the simplification finally you are going to get value T is equal to 0.83 millimeter. So this much amount of thickness of insulation we must require in order to make this material as a purely insulator or the dielectric. But if you operate more than this, then definitely this rubber is also going to behave like a conductor, and if you are going to touch this rubber, you are going to definitely get the shock. So this is the correct solution of this question. So now we are going to solve the 44th question. See the question here. The statement 1 is voltage is the energy per unit charge created by charge separation, whereas the statement 2, which is power, is the energy per unit of time. So in from these two statements we have to see which statements are correct and whether this statement 2 is the correct explanation of statement 1 or not. We need to figure out. The definition of the voltage is nothing but the amount of work done in order to bring a unit charge from infinite distance to any finite distance from a charge is called as the voltage. So listen carefully, voltage is called as the amount of work done in order to bring a point charge from infinite distance from the source to a finite distance from a source, that we are going to call it as the voltage. So voltage is equal to work by charge. So and power is nothing but it is a rate of, means you can say the amount of energy consumed in a per unit time. So therefore we are going to say P is equal to E by T. So this is called as the power and this is called as the voltage. So option or the statement 1 is correct and also statement 2 is also correct. But there is no relation between the statement 2 and statement 1. So therefore we can say these two are independent statements of each other. So therefore finally we can conclude that the statement 1 is a correct solution and the statement 2 is a correct solution, and the statement 2 is not the correct explanation of the statement 1. So option B, which is the statement 2, is not the correct explanation of the statement 1. So option B is the correct solution of this question. So now we are going to solve the 45th question. See the question here. Gauss theorem states that the total electric flux phi emanating from a closed surface is equal to. So basically the Gauss theorem is going to tell you the how much amount of total electric flux flowing or emanating from any closed surface is equal to the amount of charge enclosed by that closed surface. So out of these four options, option B, the total charge enclosed by that surface is the correct solution of this question. So let's solve this numerical. The Gauss law in the electrostatics is going to give you that information. The net amount of electric flux going outward any closed loop is equal to, we can say, the amount of net charge enclosed by that closed curve, or you can say the closed curve, or you can say the closed surface, how much amount of charge enclosed, that much amount of electric flux which is going to pass from this surface. So flux is equal to closed surface integral of d by ds bar is equal to charge enclosed by that closed surface. The unit of charge is coulomb, so therefore similarly the unit of flux is also coulomb. But if you want to convert this surface integral to volume integral, because only a closed surface can enclose a volume, so therefore closed surface integral of d by ds bar is equal to volume integral of delta d bar into dv. So this is called as the Gauss divergence theorem. But charge enclosed is nothing but it's a volume integral of rho v into dv, where rho v is called as a volume charge density, and this is the equation 2. So these both equations are equal, so therefore this volume integral should be also equal. So therefore we can say for a small amount of dv, these two values should be equal, then only these values are equal. So therefore we can conclude that delta d bar is equal to rho v. So therefore this is, we are going to call it as the differential form of the Gauss law. See, the divergence of the electric flux density is equal to volume charge enclosed, means volume charge density enclosed by that closed surface. So this is called as a differential form of the Gauss law. But this equation we are going to call it as the integral form of the Gauss law. So basically here in the Gauss law we can use any amount of Gaussian surface. You can use, based on the symmetry, we can choose any of the Gaussian surface, closed surface. So basically we are going to use only three things, which are the spherical Gaussian surface, or the cylindrical Gaussian surface, or the cuboidal Gaussian surface. So based on symmetry you can prefer any of these in order to solve the numerical in a very fast manner. See, no matter whatever the closed surface, you can take any irregular closed surface, always the net outward flow will be always equal to the charge enclosed by that closed surface. This is the meaning of this Gauss law. So now we are going to solve the 46th question. See the question here. Electric flux enclosed by a surface surrounding a charge is equal to the amount of charge enclosed. This is the statement of. So listen carefully. The electric flux enclosed by a surface surrounding a charge is equal to the amount of charge enclosed. This is the statement of the Gauss law. So out of these four options, option D is the correct solution of this question. So now I will discuss all these four options in a very detailed manner. See, Faraday's law is nothing but here. The Faraday's law is going to give you an expression of the amount of EMF induced whenever there is a rate of change of magnetic field. So whenever there is a rate of change of magnetic field, always the electric field is going to get produced in a conductor. So that we are going to know it as the Faraday's law. He has given the expression which is directly proportional to rate of change of magnetic flux. So this is nothing but here E is directly proportional to rate of change of magnetic flux. But the Lenz's law has given an expression which is whatever the EMF induced, that is going to produce the current in such a way that current will oppose the original cause. So therefore we can conclude that the cause, the effect will always oppose the cause. So therefore whatever the electric field induced, that is going to induce in such a direction that is going to oppose the cause which is going to produce. Always the effect is going to oppose the cause. So he has given expression which is negative. So you have to keep a negative expression. So therefore E is directly proportional to minus d phi by dt. So here he has given the direction of the induced EMF, whereas this Faraday's law has given the expression of the induced EMF, how much amount of voltage is induced. Whereas the modified Ampere's law, it is going to include an displacement current. So therefore modified, see, only the Ampere's law will never include any displacement current, but modified Ampere's law is going to include the displacement current expression also. It is going to include, which is closed surface integral, closed line integral of h bar dot dl bar is equal to, we can say this is called as the current enclosed This is called as a conduction current and this is called as a displacement current. These two things are going to included with the help of modified Ampere's law. And the Gauss law is going to give you an expression which is the net amount of electric flux passing through any closed surface is equal to the amount of charge enclosed. This is just now we have discussed. So therefore this is the correct solution of this question. So now we are going to solve the 47th question. See the question here. If a positively charged body is placed inside a spherical hollow conductor, what will be the polarity of the charge inside and outside the hollow conductor? So whenever you are going to keep any point charge inside this hollow conductor, then what is the amount of polarity of the charge which is inside the surface and also outside the surface, we need to figure out. So out of these four options, option B is the correct solution of this question, which is inside it will be negative and outside it will be positive. So now we are going to solve this numerical. Basically this is an hollow sphere. Inside we are going to keep a positive charge inside this hollow sphere. See, hollow sphere means it is going to have a small amount of thickness. So this is the thickness of this hollow sphere, but inside it is empty. So now based on this we have to find what is the polarity of the charge induced inside this hollow sphere and also outside this hollow sphere, we need to figure out. So therefore we can conclude that here, see, I am going to assume, always in a conductor the electric field intensity will be 0. So therefore I am going to assume a Gaussian surface. See, I am going to assume a Gaussian surface inside this hollow sphere, means we can say inside this solid part, a small amount of solid part is going to present. So from this solid part I am going to assume a Gaussian surface. So now tell me that the amount of flux passing through this closed surface is equal to closed surface integral of d bar dot ds bar is equal to the charged enclosed. But if you see clearly, this d bar at each and every point on this surface has this side this thickness. So therefore we can say inside the thickness the electric field will be 0. So nowhere wherever you are present on this closed surface, always the electric field intensity will be 0. So therefore 0 into anything is again 0. So therefore this value is equal to 0 is equal to charged enclosed. So therefore we can say the charged enclosed value must be equal to 0, but we are going to get a finite charge plus q. So there has to be opposite charge, then only the net charge will be equal to 0. So therefore we can say if this is plus q, then definitely the amount of charged enclosed inside this closed surface, or we can say inside this hollow sphere, it will be negative. Then only we can conclude that this is plus q and minus q. Overall value is equal to 0. Then only the charge enclosed is equal to 0. But always a hollow sphere or collector will be always neutral. If this is minus q, definitely this has to be positive q. Then only we can say any conductor is always neutral. So always any conductor is always neutral. If negative charge is induced downward, means definitely there has to be positive charge in the upward direction. Then only we can say this conductor is a purely neutral one. So we can see clearly negative charge is induced inside this hollow sphere and the positive charge is induced on the outside surface of this hollow sphere. Suppose if you want to draw the electric field intensity diagram from inside to the outside, suppose this distance is, let me assume this is distance is t, and this distance from here to here a small amount of thickness delta t. See, now I want to find what is the diagram of the electric field intensity from the origin to the distance at any point. See, at this point t, or we can say at this, suppose this is the radius a plus delta a, then what is going to happen is very simple, this is a plus delta a. So electric field will be always going to reduce in this manner. So up to a it will be non-zero, from a to a plus delta a. So therefore for this delta a period, this is in the inside the conductor, so therefore it has to be 0, because inside the conductor electric field is 0. Again from outward it will be again in this manner. So therefore we can see clearly inside this hollow sphere the electric field will be decreasing, but inside here in the surface that it's a solid part, so electric field is 0. Again outside still the electric field is going to get decrease in this manner. So therefore we can say this is a diagram of the electric field from center to this point, any point in space. So no matter wherever you take any point, this is the diagram of the electric field. So now we are going to solve the 40th question. See the question here. The polarization in a solid dielectric is related to the electric field E bar and the electric flux density D bar according to which one of the following relations. So basically in this question they are asking what is the relation between the electric flux density, electric field and also the polarization of any electric material. So out of these four options, option C is the correct solution of this question, which is d bar is equal to epsilon naught E bar plus P bar. So option C is the correct solution of this question. So let's solve this numerical. See here, in the polarization of any electric materials, the formula we are going to get, which is d bar is equal to epsilon naught E bar plus P bar. D bar is called as the electric flux density and P bar is called as the polarization in a solid dielectric, and epsilon naught is called as the permittivity of the free space, and here E bar is called as the electric field intensity. But the polarization is equal to N into alpha into E bar. This is an expression already I have derived in the offline class, where N is called as the number of dipoles which are going to present in a unit volume, and alpha is called as the polarizability, whereas E bar is called as the electric field intensity. But I am going to multiply epsilon naught value in the numerator and also denominator, so therefore we are going to get the previous one. But here N alpha by epsilon naught is called as the Xe, or we can call this as the electrical susceptibility. So therefore this Xe is called as the electrical susceptibility. So therefore P bar is equal to epsilon naught Xe into E bar. You can substitute this P bar in the above expression. Finally we are going to get D bar is equal to epsilon naught E bar plus epsilon naught into psi into E bar. So from these the common parts are the epsilon naught E bar. So therefore we can say, if you take these two terms outside, we are going to get 1 plus Xe. 1 plus Xe is called as the relative permittivity. So therefore epsilon naught into epsilon gar into E bar. But this value epsilon naught into epsilon gar is value nothing but which is equal to epsilon. So therefore epsilon into E bar. So therefore finally we can say D bar is equal to epsilon into E bar. So therefore all these things are going to present inside. So this is the basic expression. So from this expression we have derived the D bar is equal to epsilon into E bar. So where epsilon gar is equal to 1 plus Xi, where epsilon gar is called the relative permittivity, whereas Xe is called as the electrical susceptibility. So with the help of this formula we have derived each and everything. So this is a very important formula, and I will discuss some of the important formulas which are going to present in these dielectric materials. So this will be very useful in further examinations. Now I will discuss some of the important formulas which are present in the dielectric materials, which is divergence of polarizability is equal to polarization is equal to minus rho b, whereas the divergence of the electric field is equal to rho b plus rho f by epsilon naught, whereas divergence of electric flux density is equal to rho f, and D bar is equal to epsilon naught E bar plus P bar, just now we have discussed, and epsilon gar is equal to 1 plus Xe, this also we have discussed, and D bar is equal to epsilon into E bar, where epsilon is called as a epsilon naught into epsilon gar, and also P bar is equal to epsilon naught into Xe into E bar. See, all these formulas we have discussed just now. So these are the very important formulas which are going, so based on this definitely they are going to ask in any examination. And also here rho b is called as a bond volume charge density and rho f is called as a free volume charge density. So these are the important expressions. Already I told you D bar is equal to epsilon naught E bar plus P bar. Now I will discuss this one in the another format also, which is, see, epsilon naught into E bar, we are going to call this as, this term is going to, we are going to call this term as called as the flux density due to free charges. This term we are going to call it as the flux density due to free charges, whereas this term we are going to call it is either polarization or also we are going to call it as flux density due to bond charges. This term is because of the free charges and this term is because of the bond charges. So therefore this is we are going to add. So therefore definitely we are going to call this as the net flux density or the total flux density. So total flux density is a summation of the flux density due to free charges and also the flux density due to bond charges. So therefore this is the correct expression of this question. So you have to remember all these formulas. So based on these formulas definitely they are going to ask one expression from these questions. We are going to solve the 49th question. See the question here. Point charges of minus 10 nanocoulomb and 10 nanocoulomb are located in free space at minus 1, 0, meter and also 1, 0, meter respectively. So what is the energy stored in the field? So there are 2 point charges and also they are given the charge values which are the minus 10 nanocoulomb and 10 nanocoulomb, and also they are given their position in the 3 coordinate axis. So based on this we have to find what is the net amount of energy that is going to present in the electric field between these charges we need to figure out. So out of these 4 options, option C, which is minus 450 nanojoules, is the correct solution of this question. So let's solve this numerical. Before I teach that concept, let me tell you a small example. Suppose there is an arrow. Suppose if there is an arrow, you want to throw it. So definitely you are going to keep it here and you have to stretch the arrow outward, means you are going to do some amount of work in order to pull this arrow backward. See how much amount of work you are going to do, that much amount of energy is stored in that arrow. So therefore we can see how much amount of work you are going to do in order to pull the arrow backward. That much amount of energy is going to stored in that arrow, and whenever you are going to release it, that much amount of energy is stored and it is going to released outward. So whatever the work you are going to do in order to keep the charges is equal to the amount of energy stored. Suppose there is a system. So in this system, I am going to keep the charge Q1 inside. So before the charge Q1 I am going to keep inside, there is nothing source of empty. It indicates that we can easily bring this charge Q1 inside this system because there is no amount of repulsion force is going to present inside that system. So therefore we can say the amount of energy in order to bring this Q1 into the system is 0, because you can easily keep that charge inside because there is nothing charge present inside already. But if you want to bring the charge Q2, but already there is a charge Q1 from the previous one, so definitely you have to do some external work, means you have to do something against to that force. So you are going to do some work. So work is equal to nothing but here this charge into the potential at that point because of the charge 1. So therefore we can say the amount of work done in order to bring a charge Q2 into the system is equal to charge Q2 into voltage of 1 at the point 2. So V1 2. See how much amount of work we are going to do, that much amount of energy is stored. In the previous case the energy stored is 0, or we can say the work done is 0, but in the previous case the amount of work done is Q2 into V12, or we can say the amount of energy stored is Q2 into V12. So now I want to find what is the net amount of energy stored, which is summation of this first and the second case. So therefore U is equal to U1 plus U2, U1 is equal to 0 and the U2 is equal to Q2 into V12. So 0 plus Q2 into V12 is nothing but Q2 into V12. So Q2 into V12 is nothing but voltage of charge Q1 at point 2. So Q1 by 4 pi epsilon R12. So definitely you are going to get Q2 into Q1 by 4 pi epsilon R12. But this is the final expression. So this is the net amount of energy, or we can say this is the net amount of work done in order to bring the two charges, or we can say that net amount of energy stored in this field. So now Q1 is equal to, in the question they are given, which is minus 10 nanocoulomb. It is present at a point of minus 1, 0, 0. And similarly Q2, it's a charge of plus 10 nanocoulomb. It is going to present at 1, 0, 0. And also in the question they also given this is a free space. So therefore relative permittivity value is equal to epsilon r is equal to 1. So now I want to find what is the distance between the charge Q1 Q2, which is under root over 1 minus of 1, which is 1 plus 1 whole square plus 0 minus 0 whole square plus 0 minus 0 whole square. So if you do this one, we are going to get 2. So now we know each and everything, just blindly substitute all those values in this above expression. So Q1 is nothing but minus 10 into 10 to the power of minus 9, Q2 is 10 into 10 to the power of minus 9 into 1 by 4 pi epsilon naught value is equal to 9 into 10 to the power of 9, and R12 value is 2. So if you solve this one, we are going to get the amount of energy which is going to present in this field, which is minus 450 nanojoules is the correct solution of this question. So now we are going to solve the last question of this lecture, question number 50. See the question here. A parallel plate air capacitor as shown below has a total charge Q and a breakdown voltage V. A slab of dielectric constant 6 is inserted as shown. The maximum breakdown voltage and the charge at this voltage respectively would be. So basically in this question they have given a capacitor, parallel plate capacitor, and they are going to insert this slab of dielectric constant 6. Then what is the net amount of charge and also the net amount of voltage, the maximum voltage that is compared with the previous one we need to compare. So out of these 4 options, option A is the correct solution of this question. So let's solve this numerical. So now here is a parallel plate capacitor. For this parallel plate capacitor of length L and W, so therefore we can say a charge Q is going to present on the plates, and also D is the distance between the plates, and V is the voltage across the plates. So we are going to give a supply voltage of V. So now based on this data I want to know what is the capacitance. I am going to assume this as the first case, or we can say old version. So C old is equal to epsilon naught is a air. Basically this is a air. So therefore here epsilon r value is equal to 1. So therefore epsilon naught A by D. So therefore we can say capacitance is equal to charge by voltage, so Q by V, where A is equal to area of this plate, which is L into W. Suppose I am going to insert an dielectric in this manner of slab with a constant epsilon r value is equal to 6. If I am going to insert for half of the length, then what is the net amount of charge is going to present, and also the net amount of breakdown voltage we need to figure out. So now here this is now these two capacitance, because the electric field always goes from positive charge to negative charge, and the electric field is parallel to the dielectric interface. So whenever the electric field is parallel to the dielectric interface means the capacitance are arranged in a parallel manner. But whenever the electric field is normal to the dielectric interface means the overall capacitance will be a series combination. But here the electric field is parallel to the interface of the dielectric, so therefore we can say blindly these two capacitors are connected in a parallel manner. So net capacitance is equal to summation. Whenever the capacitors are connected in parallel, the overall capacitance is the parallel means summation C1 plus C2, where C1 is the capacitance due to dielectric and C2 is the capacitance due to air medium. So C1, I want to find what is the capacitance due to dielectric medium. So epsilon naught into epsilon r into area is only this part, so L by 2 into W by distance is D. So epsilon r is equal to 6. So 6 into epsilon naught into LW is L into W is nothing but A. So A by 2 into D. So this is the value of C1. But C2 is the capacitance due to air. So therefore we can say epsilon naught into epsilon r is value 1 into area L by 2 into W by D. So therefore now L into W is nothing but A. So epsilon naught A by 2 into D. If you want C nu, you have to add these two ones, C1 and C2. If you add these two quantities, we are going to get 3.5 into epsilon naught A by D. But epsilon naught into A by D is nothing but which is C volt. So therefore 3.5 into C volt. So C nu is equal to 3.5 into C volt, but C nu is equal to Q nu by V nu. So Q nu by V nu, 3.5 into C volt is nothing but Q by V. So Q by V, if you substitute and if you compare, we are going to get finally this is 3.5 into Q by V. So if you compare, we are going to get Q nu is equal to 3.5 Q and V nu is equal to V. So therefore we can say Q nu is equal to 3.5 Q and V nu is equal to V. So this is the correct solution of this question. Means if you are going to insert a dielectric in this capacitor, definitely the charge is going to increase and the voltage is going to remain same as the previous one. So by this lecture we have successfully completed the 50 questions of EMT of previous year questions of IES of electrical engineering in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever we upload a new video the direct notification comes from mobile. If any improvements in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.